Speaker again. Next we have Jonathan Shafer, who's speaking about a direct sum result on the information complexity of learning.
Hi, thank you. And today I want to talk with you about a joint work I did together with Nachum and Amir Yehudayoff from the Technion. And I want to start off my talk with a basic, simple, I think fairly central intuition in learning theory. And the intuition is that learning and data compression are very closely related tasks. They might actually be equivalent in some senses. And you can think about it this way. If you want to compress some data set, what you're basically going to do is you're going to look for patterns in that data set that repeat, and you're going to use those patterns to create a more concise representation. On the other hand, in learning, what you want to do is you want to identify patterns in a training set, and hopefully you can use those patterns to make predictions about an unseen test set. This is also related to the philosophical idea of Occam's razor that says that when we want to make predictions about the physical world, we prefer to choose the most concise theory that is consistent with the observations we've seen so far. And it has some useful applications in the sense that it allows us to employ tools from combinatorics and information theory and apply them to learning theory, whereas they might not have been originally applicable. So this intuition has been mentioned a number of times during the talks today and previous days. Has been formalized by various people in various times. Occam learning in the 80s and minimum description lengths in the 70s. And I wanted to delve slightly a bit more into detail in one of these formalizations, which is called sample compression scheme. In sample compression schemes, basically we have an algorithm that operates in two stages. In the first stage, it receives some sample with m data points, and it chooses some subsample from that sample, let's say of only 3 points. And the second stage, it chooses some generalization, some function based only on that subsample, and that function needs to be consistent with the whole original sample. And it turns out that if you can do this, if you have an algorithm that has a constant size compression scheme, then if you have a class that has a constant size compression scheme, then that class is learnable. That was proved in '86 by Littlestone and Warmus. And 30 years later, the converse was proved, which shows that if a class is learnable, let's say it has VC dimension D, then it also has a constant size compression scheme that is exponential in D. So in that sense, we see that learning and compression are essentially, they're essentially equivalent in the sense of sample compression schemes. But if you think about it, how do you, let's say, if I as a human want to learn, let's say, what a cat is, I don't necessarily remember any specific example of a cat. I might have seen many, but I don't remember any specific example. I remember some idealized version, let's say Garfield, which is, I don't know, fat and lazy and likes to eat, yeah? So that's what I'll remember. So what we wanted to do is we wanted to take that idea and say, okay, how can we modify sample compression schemes? So what we did is we said, instead of remembering a specific number of examples, we can remember whatever we want, any processed representation, so long as we only remember a small number of bits from the examples that we've seen. So formally what we require is that the algorithm have only a small mutual information between the input sample and the output hypothesis. And it turns out that when you use this requirement, you can get some nice results. Basically, if you control the mutual information between the input and the output, that gives you guarantees about the generalization error of the algorithm. And if you think about it, that actually, it makes sense, because if you have a mutual information that is on the order of the number of samples, that means you can remember something from each sample. You can basically memorize the input training set. And then you might not generalize well. On the other hand, if your if your mutual information is a lot smaller than the number of samples, then you have no chance of memorizing. You can't overfit in that sense. So this theorem, which we proved in a previous paper, and some other people have proved fairly similar results also, is useful in a number of ways. Also, it allows you to prove generalization guarantees on cases where you want to prove the generalization guarantees for specific distributions, or a specific set of distributions, or a specific function, or for learners that are not UAM or non-proper learners. So in this situation, we have a number of questions that we can ask. One of them is, what about the convents? We saw that if you have compression in this sense, you have learning. Is the convents also true? Another question is, how does compression schemes in this sense relate to the classical sample compression scheme? Are they the same? Are they different? And more generally, we would like to understand how this quantity, the mutual information between the input and the output, how does it behave? So in order to answer that question, we introduce a fairly straightforward definition, which is the information complexity of learning. And this is analogous to information complexity and communication complexity. And basically what it says is that every algorithm has a cost, which is the amount of information that you can make that algorithm use with the worst distribution possible. And then the information complexity of a class of functions is the cost of the cheapest algorithm for that class of functions. So that's the information complexity. Let's look at a very simple example. So if we have a class of thresholds, simply monotone increasing functions from some subset of the natural numbers to 0, 1, then it turns out that the information complexity of this class is log n, where n is the size of the interval. So if we take this result, this already answers to the first two questions that I mentioned. So is it true that learning and compression are equivalent? So the answer is no, because the information complexity of thresholds is as large as we want. We can make the interval as large as we want, so the information complexity is not bounded, but it's very easy to learn thresholds. So it doesn't turn out to be equivalent in that sense. And is it true that sample compression schemes in the classical sense turn out to be the same as compression in this sense? So again, the answer is no, because we have a sample compression scheme of size 1 for thresholds, while again here we can make the information complexity large. And now I want to discuss this last question of, in general, what can we say about the information complexity of learning? So a partial answer is given by this theorem, which says basically that for every natural number d, we can construct a class of hypotheses that has VC dimension d, and the information complexity will be d log n. N is the size of the x. If you have a class of hypotheses, so they map from x to y, so n is the size of the x. Okay, so one of the interesting points about this theorem is that in order to prove it, we had to basically prove a direct sum result for information complexity. And basically, the proof outline is the following. We start by defining a product operation on hypothesis classes. So if you take two classes of hypotheses, you can somehow combine them to get a third class that puts them both together. Then you can prove a direct sum result, which says the information complexity of the product class is pretty much equal to the sum of the information complexities of the individual classes. And finally, you can apply that direct sum result to thresholds, to the class of the threshold multiplied by itself d times. And you get a class that has VC dimension d and information complexity d log n. That's it. Thank you very much.
Great. Manfred.
Yeah.